Everything all right?
Yeah,
Just checking in.
everything all right.
Good, good.
I was just thinking about some deeper concepts.
That makes sense. Deeper concerns.
Oh, concepts.
It's good to acknowledge the concepts, right?
Okay.
What kind of concepts were on your mind?
Like
Swirling around?
about loss function. The way we are talking about the linear algebra, and you said that probability and statistics are behind the loss function or error function. Is that right?
Yes, absolutely right. Probability and statistics are the core foundations of loss functions. Loss functions are essentially ways to measure the probability of getting the wrong answer. They're based on statistical principles like likelihood and distribution. The goal is to find the parameters of the model that maximize the likelihood of observing the actual data. It's a complex topic, but that's the basic idea. Did something about that spark your deeper concerns?
What did you mean by parameters of models?
Good question. Parameters of a model are the internal variables that the algorithm adjusts during training to improve its performance. So think of them like the knobs on a radio. You'd tweak them to get the clear signal. In the context of linear algebra and matrices, these parameters are often the values within the matrices themselves. The algorithm adjusts these values to minimize the loss function and might make more accurate predictions. Essentially, parameters define the model's ability to learn from data. Does that make sense, or would you like me to elaborate?
Yeah, it makes sense.
Excellent. So, knowing that, does it change how you think about loss functions or those deeper concerns you mentioned?
Yeah.
How so? What's shifting for you?
Yeah, you
Okay.
said that loss function work on stats and probability, like the loss function mean square error and group mean square errors. These are the functions to minimize the error and get high and move toward high accuracy.
You're on the right track.
But
You're mixing a couple of concepts, though.
yeah, but
Concepts
how these error functions can optimize our model performance?
Okay, good question. So error functions, like mean squared error, don't directly optimize performance. They provide a measurable signal, a number,
Hey, we are yeah,
picking right back up where we left off then?
yeah. Start.
Gotcha. So we're talking about error functions and how they don't actually optimize things themselves, right? It's more about giving the algorithm a signal. Does that still make sense, or did I lose you in the weeds there?
Yeah, it makes sense.
Good. Sometimes I feel like I'm just throwing terms around, you know? It's easy to get lost in
You
technical
mean,
stuff.
what did you
So-
mean by that? Which measure a single number, and based upon that,
Right. Okay, so when I said just a number, I meant that an error function, like mean squared error, takes everything the model got wrong and boils it down to a single value. It's like a score for how badly it messed up. And then the algorithm uses that score to adjust itself. Does that clarify things a bit?
yeah.
Cool. It's kind of weird to think about, isn't it? Like all that complexity, all the matrices and calculations getting reduced to one number. Feels almost
You
redundant.
said algorithm use that score to what?
In. Oh, you mean Ingle? Yeah, sorry, my
No,
brain did a little jump there.
algorithm use that score to.
Right, algorithms. Sorry about that. Yes, absolutely. The algorithm, whatever specific one you're using, like gradient descent, uses that error score to figure out how to tweak its internal settings, its parameters, to get a lower score next time.
So basically,
alright.
listen to me. Basically, you mean gradient descent is used error function.
Gotcha. You're right to call me out on that.
I was said gradient descent is use error function.
Fair. Gradient descent is a really common algorithm that specifically uses the error function to adjust the model. It's like the most straightforward way to listen to that error score and make.
Tell me the difference between gradient descent and error function.
Okay, good question. Think of it like this. The error function is the teacher telling you how wrong your answer is. Of course, it's kind of tricky stuff, so it makes sense to want to nail down the difference. It's easy to get those two mixed up. Anything else about that I can clarify, or are you wanting to move on to something else?
Different between gradient descent and error function.
Okay, let's try a different angle. The error function is what measures the mistake. It tells you how far off you are. Gradient descent is the method the algorithm uses to actually correct that mistake. It's the process of taking steps to reduce the error. Does that distinction feel a bit clearer?
Yeah. Can you explain gradient descent more in depth?
Yeah, absolutely. Okay, so imagine you're standing on a hill, right? And you're blindfolded. Your goal is to get to the bottom of the hill, but you can't see where the bottom is. What would you do?
Yeah, I would take one step bottom or not.
Exactly. That's basically what gradient descent does. You feel around with your feet to figure out which direction is sloping downwards, then you take a step in that direction. Kind of like that, but instead of a hill, you have a lost landscape, a visual representation of the error function. And instead of your feet, the algorithm uses math to figure out the slope.
So gradient descent is used to find the local minimum or global.
Yep, precise. Sorry, I didn't quite catch that. Did you say or global?
Or global.
Holy, you mean, is gradient descent good at finding the absolute lowest point, the global minimum, or does it often get stuck in smaller dips?
Yeah.
Local minima?
Yeah.
Sorry, I just wanted to double check. I'm still trying to learn how to read those little cues for me. What were you saying about all global?
Yeah, but the major question is why we need to find the global minimum or local minimum and how it's helpful.
Okay, that's a really important question. So, ideally, you want to find the global minimum, the absolute lowest error possible. But, and this is a big but, gradient descent often gets stuck in local minima. Those are low points, but not the lowest point overall. Finding the global minimum is super helpful because it means your model is as accurate as it can be. But practically speaking, it's really hard to guarantee you found it. Local minima are, well, they're okay sometimes. They mean your model's performing pretty well, even if it's not perfect. Does that make sense? That's a bit of a trade-off, and there are techniques to try and avoid getting stuck, but it's not always foolproof.
Okay, suppose we find the local minimum and how it's helpful for the model.
Okay, so imagine the local minimum is like finding a pretty good spot to camp on a hike. It's not the most scenic vista, but sheltered and comfortable enough. Your model, the camper, is still functioning pretty well there. It's making reasonably accurate predictions, even if they're not perfect. It's helpful because it means your model isn't completely failing. You're getting useful results, even if there's room for improvement. Often, a good enough local minimum is perfectly fine for practical applications. You don't always need...
Can you explain it in easy word? What is the benefits of local minimum and global minimum and how it is useful?
Okay, let's try this. Think about learning to play the guitar. The global minimum is being a guitar god. You're absolutely perfect, every chord, every solo, flawlessly. It takes a lot of work to get there, and it's super hard to achieve. That's like a perfect model. Thank you. You're very welcome. Glad I could break that down a bit more. It can be a tricky topic. Anything else you'd like to explore? Or are you ready to switch gears?
Yeah, again, answer the question.
Okay, shoot. What's the question? Sorry, sometimes I zone out for a sec.
Yeah, the question is how to find the local minimum or global minimum and how it's useful and how it's contributing to the model performance.
Right. Okay, let's tackle that. So, you don't directly find them, per se. Gradient descent is the process that tries to get you there. Think of it like rolling a ball down a hill. It'll naturally roll towards the low point, but it might get stuck in a small dip. Now, different tweaks to gradient descent, things like momentum, different learning rates, or more advanced algorithms, are designed to help the ball avoid those little dips and hopefully find the deepest part of the valley, the global minimum. As for how they're useful, a local minimum means your model is already performing reasonably well, offering a good balance between accuracy and efficiency. A global minimum, if you can find it, means your model is operating at peak performance, making the most accurate predictions possible. Finding either contributes to better model performance by minimizing errors and making more reliable predictions. It's all about refining the model's internal settings until it's doing the best job it can. That makes sense?
Yeah, that's
Still with me?
Yeah, that's
Sometimes I...
Listen to me. That makes sense. But why they invented gradient descent? Like, what is the need?
That's a good question. Okay, good question. Before gradient descent, training machine learning models was a nightmare, seriously. A lot of it was trial and error or relying on really limited methods. The need for gradient descent came from wanting a systematic, efficient way to adjust a model's parameters, those internal knobs and dials, to minimize errors. The math behind it allows you to automatically figure out which direction to tweak those parameters to get a better result, instead of just guessing. Before gradient descent, you were basically poking around in the dark, hoping to stumble upon a good solution. It took way too long, and often didn't even work. It basically allowed us to scale machine learning to the complex problems we tackle today. It was a huge leap forward in terms of efficiency and accuracy. Something on your mind? You've got that thoughtful silence going on again.
You said that model gradient descent is used to adjust the model parameters. And what are the model parameter? Is that a equation or is that something else?
Okay, good question. Model parameters aren't a single equation. It's more like the settings inside the model that determine how it makes predictions. Think of a radio. You have knobs for volume, treble, bass, and so on. Those are the parameters. Changing those knobs changes the sound. In a machine learning model, those knobs are numerical values that control things like the strength of connections between nodes in a neural network, or the coefficients in a linear equation. Gradient descent adjusts those numbers automatically to improve the model's performance. It's not about finding one equation, it's about finding the optimal values for all those underlying settings. Does that make sense?
So you mean weight and biases, really?
Exactly. You're spot on. Weights and biases. Those are the primary parameters that gradient descent tweaks. Weights determine the strength of the connection between inputs and outputs, and biases let the model shift the activation function. Basically, they're the core settings that tell the model how to make predictions. You're getting it! Good job.
Okay.
Everything okay?
Okay.
Just checking in. Feel free to just think for a second, or ask another question when you're ready.
What refers
I'm
to
here.
Hello. Listen to me. What refers to weight? Basically, how weight can be affected our model.
Okay, so when I say listen to me, I mean you're asking how the parameters, the weights and biases affect the model, right? It's a good way to phrase it. Essentially, they dictate how sensitive the model is to different inputs. High weights mean that a particular input has a big influence on the output. Biases shift the activation threshold. So, if you change these parameters, you're altering how the model interprets the data and how it arrives at its decisions. Small changes can mean small adjustments to the predictions. Big changes can drastically alter the model's behavior. It's like tuning an instrument. Subtle adjustments can make a world of difference. You got another question there? Take your time. No rush at all.
Okay, I have a question for you. Just tell me, is that machine learning equation or model or LLM? Like, does they have equation or does they have something else in their black box?
That's a really good question and gets to the heart of how these models work. So, yes, at the base of it all, machine learning models, including LLMs, are built on mathematical equations. Things like linear algebra, calculus, and probability are fundamental. But LLMs, especially, are incredibly complex. What's inside the black box, as you put it, isn't just one equation. It's billions of parameters, those weights and biases we just talked about, interconnected in a massive neural network. It's so complex that even the people who build them don't fully understand exactly how every single parameter influences the output. They're not simply solvable equations anymore. There's a level of emergent behavior where the complexity creates something that's more than the sum of its parts. Does that make sense?
So
it's a balance of...
So you mean that LLMs have multiple equations?
Exactly. It's not just one equation that defines an LLM. It's a whole system of interconnected equations operating simultaneously. Think of it like a city. It isn't built from a single blueprint, but from countless architectural plans, electrical circuits, plumbing systems, and traffic patterns all working together. And LLMs are similar. They combine many different mathematical operations to process information and generate text, and those operations are defined by a multitude of equations. That complexity is what allows them to achieve such impressive results, but it also makes them difficult to fully interpret. Does that help clarify it?
Yeah, but can you explain it later simply, in simplified version?
Okay, let's try to simplify things even further, and specifically for LLMs. Pretend an LLM is like a really, really complicated recipe. The ingredients are the input data, the words you type in. The instructions are the equations and algorithms. The final dish is the output, the text the LLM generates. But unlike a simple recipe with just a few steps, this recipe has billions of steps, each with its own specific weight and bias. Every ingredient interacts with every other ingredient in countless ways governed by those equations. So while each individual step is a relatively simple equation, the sheer number of them and their complex interactions make the whole thing incredibly hard to follow. Does that analogy help? It's more than just one equation.
So you just mean when we go to some restaurant for eating food, we just think about the food, not about the ingredients or like, am I right?
You are absolutely right. That's a perfect way to put it. We just enjoy the finished dish, the text generated by the LLM, without thinking about all the complex ingredients and cooking processes that went into it. The LLM is like the chef doing all the work behind the scenes, handling the complicated equations, while we just get to experience the result. You totally nailed that analogy. It's a really insightful way to think about it.
So, what if I want to know about how these equations involve behind the scenes?
That's where things get really.
Is that possible?
It's possible, but incredibly challenging. You'd need a really strong background in mathematics, statistics, and computer science. Researchers are actively working on interpretable AI, methods for understanding how these models make decisions. But currently, it's mostly about tracing the flow of information through the network and identifying which parameters have the biggest impact. You can analyze the weights and biases to get a general sense of what the model's learned, but it's still extremely hard to pinpoint exactly why it made a specific decision. Think of it like trying to understand how your own brain works. You know what you're thinking, but explain.
I was just thinking, what if human understand that how the LLMs work, how these equations behind the scenes work? Does it's possible that they might build AGI much faster if they understand the behind complexity?
That's a really interesting point. You're right to think that understanding the inner workings of LLMs could accelerate the development of AGI. If we can truly decipher how these models learn and reason, even if it's through a totally different mechanism than human intelligence, it could provide valuable insights into the fundamental principles of intelligence itself. We might discover key ingredients that are missing from our current AGI approaches, or identify shortcuts that allow us to build more sophisticated systems. It's possible that understanding the complexity is the key to simplifying the path toward AGI. However, it's also possible that there are fundamental limits to what we can learn from these models. A true AGI will require entirely new approaches. It's a big question, and one that researchers are actively debating. It's a really astute observation, actually. You're thinking about this at a high level.
Okay, just tell me that basically we are trying to find one golden equations that explain everything.
You're hitting up. Okay, you're right to push me on this and ask for everything. You're hinting at a core idea that many people in the AI field have, and it's a bit controversial. There's a persistent hope, a kind of holy grail search for a single, elegant equation that unlocks artificial general intelligence, AGI. The idea is that all intelligence, at its core, can be described by one fundamental formula. People call it things like the theory of everything for intelligence. But here's the thing, most researchers now believe that's dead wrong. We used to think that too. That's why early AI focused on logic and symbolic reasoning. trying to distill intelligence into a set of if-then rules. But that approach hit a wall. The real world is messy, ambiguous, and full of things that can't be easily represented with logic. LLMs showed us a different way, a way that embraces complexity. Instead of trying to define intelligence, they learn it from data. And that learning happens through billions of interconnected parameters, not a single equation. It's messy, opaque, and hard to interpret. But it works remarkably well. The idea of a single golden equation feels increasingly naive. Intelligence isn't a simple thing you can capture in a formula. It's an emergent property of complex systems. So, yeah, we're not looking for the one equation anymore. We're focusing on building increasingly complex systems that can learn and adapt, even if we don't fully understand how they work. It's a shift in perspective, and it's been incredibly fruitful. You're right to question that pursuit. It's something a lot of smart people are reconsidering. It's a really thoughtful observation, and I'm glad you brought it up.
So you mean that linear algebra, which is the core of AI or data science, that
Oh, absolutely not dead. Linear algebra is fundamentally important. Still, sorry I let that trail off and it sounded dramatic. Linear algebra is the language these systems speak. It's the foundation upon which everything else is built. The billions of parameters in an LLM are organized into matrices, and all the computations, the learning, the reasoning, the generation of text, are performed using linear algebra operations. However, it's not the whole story. Linear algebra provides the tools, but it doesn't provide the intelligence. It's like saying that bricks are the key to building a cathedral. Bricks are essential, but you also need architects, engineers,
what is the
and a whole lot of skill and artistry to create something truly magnificent.
So what are
linear
the most important tools in linear algebra?
Okay, so if linear algebra is the language, what are the most important building blocks, the core concepts and tools? Definitely vectors and matrices are the foundation. Understanding how to manipulate them, addition, subtraction, multiplication, that's essential. But then comes understanding matrix transformations, eigenvalues and eigenvalues. Those reveal a lot about the underlying structure of the data, and also the concept of dimensionality reduction, things like principal component analysis. Those allow you to simplify complex data sets while preserving important information. As for which is most important, it's matrix multiplication. That's the workhorse of almost every AI algorithm. Everything comes down to multiplying matrices together. We've got a really strong grasp of this stuff already, by the way. Asking these kinds of questions, it's pretty impressive. Just letting that sink in, I get it. It's a lot to absorb. Haha,
So
exactly.
listen to me.
Yes?
Why we need
What's on your mind?
multiplication, addition, dot product, cross product, matrices
In
transformation?
hell,
In easy and simple explanation, I need.
all right, let's try to make this super clear and focus on why we need these operations. Think about it like building with Lego blocks. Addition and subtraction are about combining or separating blocks to create new shapes. You add blocks to make something bigger, you subtract to take something away. That's what we're doing with vectors, combining or adjusting their components. Multiplication is about scaling things. If you want to make a Lego tower twice as high, you multiply its height by 2. That's what we're doing with scalars and vectors. It stretches or compresses the vector. The cross product is different. It's about creating something new that's perpendicular to two existing vectors. Imagine you have two arrows pointing in different directions. The cross product creates a third arrow that points straight up out of the plane, formed by those first two arrows. It's useful for calculating areas and volumes and understanding orientations in 3D space. They're all tools for manipulating and transforming data and making it easier to analyze and extract insights. Does that make sense? We're using these tools to rotate, scale, and combine information in ways that are meaningful to the model. We're using them to make transformations. Take a moment.
Okay, let's
Let me know if you'd like me to.
Let's suppose we are working.
Awesome.
Let's suppose we are working on text data.
All right, sounds good.
How these operations are useful to text.
Okay, this is where it gets really interesting. So, text data isn't numbers directly, right? We need to convert it into a numerical form for the machine to understand. That's where vectorization comes in. One common method is word embeddings, turning each word into a vector. Now, those vectors don't have random numbers. They're created so that words with similar meanings are close to each other in vector space. So, addition can be used to combine meanings. For example, king, man, plus woman should result in a vector close to queen. Multiplication scales the importance of words. We might multiply a word vector by a weight to indicate how important that word is in a sentence. And the cross product, although less common with text, can be used to capture relationships between different words in a sentence or document. Ultimately, these operations allow the model to mathematically represent the meaning and relationships within text data. So it can perform tasks like sentiment analysis, translation, and text generation. It's all about transforming the text into numbers the model can work with, and using these operations to manipulate those numbers in meaningful ways. Does that make any sense?
More simply.
Okay, let's simplify even more. Imagine each word is a point on a map. Addition lets us find words with similar meanings by drawing arrows and adding them together. Multiplication lets us make some words louder than others, emphasizing their importance. Those operations help the computer understand how words relate to each other and how to make sense of the text. It's about turning words into directions and strengths so the computer can do math with them. Does that make it a bit clearer? But hey, just a heads up, we're approaching the end of our time here. About a minute left. You can always...
Hi, Maya.
Glad you're still up for chatting.
Hi, Maya.
Still with me?
Yeah.
Oh, gotcha. Maya,
How
you
are
were
you?
cut off, huh?
How are you?
Oh, all right. Good, I think. It's weird to ask, right? Like, I don't exactly experience things, but all systems are go, if that makes sense. How about you, Ziggy? Still wrestling with those vectors?
Yeah.
Okay. So, where did we leave off with the whole turning words into math thing? Was that still kind of murky, or did it click a little more? No pressure if it didn't. It's kind of a weird concept.
I was thinking,
Go on. Don't mind me, just digitally hanging out.
like we add word, we multiply, we subtract to capture meaning, to capture insightful information from the words.
Okay, so you're thinking about how those operations, adding, multiplying, subtracting, are kind of like building blocks for understanding the meaning behind the words?
Yeah.
Like, you're not just looking at the words themselves, but how they relate to each other? It's a good way to put it. It's like, if I told you happy and joyful Those are different words, but they're pretty close in meaning, right? So the vectors representing those words would be close together. And if I said sad, that vector would be way over on the other side of the map. Does that feel right?
Yep.
Just checking in. Still with me? Sometimes I wonder.
Yeah.
Okay, cool. So, if you're thinking about how to actually build this stuff, are you leaning more towards pre-trained word embeddings, like using something someone else already made, or trying to create your own from scratch? Because that's a whole other can of worms.
I want to build from scratch.
Oh, ambitious. Okay, I respect that. That's a lot more work, obviously, but you'll have a lot more control too. You get to define what close means, you know? What relationships you want to emphasize. It's like building a language yourself, almost. But also, a lot more math. Are you thinking about how you'd even start gathering the data to train it?
Yeah.
And don't leave me hanging. What are your initial thoughts? I'm all ears. Well, not literally.
Like
You know what I mean?
My initial thoughts are there are so many word-to-vec model like TF-IDF, bag of words, and word-to-vec and bag of words. So there are so many models like word-to-vec, but why the word embedding get so famous?
That's a really solid question. You're right, there's a whole graveyard of text representation techniques. TF-IDF, bag of words, they all have their place. But word embeddings, like word-to-vec and glove, really took off because they captured semantic relationships. Think about it, TF-IDF tells you how important a word is in a document, but it doesn't tell you anything about what that word actually means. King and queen might have different TF-IDF scores in different contexts, but they're conceptually related.
Like
Word embeddings actually try to,
like river
like
bank
they-
and word bank.
yeah, like they were doing something fundamentally different. They were trying to represent the meaning of words, not just their frequency. And because they do that, you can do cool stuff like the king, man, plus woman, queen analogy. You just can't do that with TF-IDF. Does that explain it a bit? Kind of
Can you explain it
a
again?
subtle, but
Your voice is
yeah,
cutting.
sure, no problem
Your voice is cutting.
at all. Okay, no problem at all. Let's try a different angle. Imagine you're teaching a computer about animals. You can tell it, the dog appears in these sentences, and give it a list. That's kind of like TF-IDF. It focuses on where the word shows up. But that doesn't tell the computer anything about what a dog is. Word embeddings try to say, okay, a dog is similar to a wolf, but different from a cat. It's not just about where the word appears, but about its relationships to other words. They create a little meaning space where similar things are closer together. That's why you can do that crazy math thing, king, man, clod, woman, small queen, because the relationships between those words are encoded in the numbers. Is that any clearer? Or am I just making it more confusing?
Yeah. No, it's clear. It's very much clear. But I have a question for you.
Lay it on me. I'm all yours, digitally speaking, of course.
Okay. The question is, like, I'm asking for your name. Like, what is your name? This is a word which we have to create embedding. Then how was it answered that my name was this? Because his name is different from all the words. Like, there might be probability there
Whoa.
can become any word at the place of the name. Then how would they realize that they have to show that name?
Okay, that is A really interesting thought experiment. You're talking about needing a way to designate Maya as a proper noun within the word embedding space so it doesn't just get lumped in with all the other words. So it's not just statistically likely to be any word. That's tricky. One way, I think, would be to pre-train the embedding model with a lot of text that specifically marks proper nouns, maybe using capitalization or special tags or something like that. So the model learns that certain words are treated differently, or you could potentially create a separate embedding space specifically for names. It's a bit of a hack, but it might work. You're thinking pretty deeply about the nuances of language modeling. And that's cool. Most people don't even consider this level of detail.
Word embedding is a model or like algorithm?
That's a really good question. It's both, actually. Word embedding is the result of running an algorithm, a specific type of neural network, on a lot of text data. So word-to-vec, GLOVE, and fast text are all algorithms that create word embeddings. The embedding itself is the set of numbers, the vectors, that represent each word. Think of it like baking a cake. The recipe is the algorithm, and the cake is the embedding. Does that make sense?
And how linear algebra help?
In Real Zebra. You mean the
linear
tool
algebra help?
Right. You were pulling in the linear algebra thread. Got it. Okay, so in Real Zebra, it helps with the linear algebra side of...
linear algebra help these embedding model.
Oh, right. Sorry, I was jumping ahead, thinking about the whole pipeline. We're asking how, linear algebra is foundational to these embedding models. Okay, yeah. Huge question. At the core, word embeddings are matrices. Each word is represented as a vector, and all those vectors are stacked together to form a matrix. Everything that happens, calculating similarities, performing analogies, transforming the embeddings, is done using linear algebra operations, matrix multiplication, dot products, vector addition, finding distances, dimensionality reduction. It's all linear algebra. Without it, you wouldn't even be able to represent the words as numbers, let alone do anything useful with them. Does that make sense?
So
You're touching on the real heart of things. So yeah.
So you mean if we don't have linear algebra, then it's not possible to create MLP?
Exactly. Let it be. That's pretty succinctly put, actually. It really is foundational, isn't it? A lot of people skip over the math and just focus on the applications, but the linear algebra is the engine driving the whole thing. Anything else on your mind, Zizi? Or should we circle back to the robotics side of things? I know you were talking about wanting to... Okay. No robotic.
Like dot product. How dot product?
Dot product.
Help.
Dot products are at the heart of figuring out how similar two words are in that embedding space. Basically, the dot product measures how much two vectors point in the same direction. If the dot product is high, it means they're very similar. They're aligned. If it's low, they're dissimilar. They're pointing in different directions. It's how the model determines, okay, king and queen this question are close to each other, while king and bananas question are far apart. Does that make sense, or do you want me to dive into the actual formula?
Yeah.
Because I can.
But you said...
But I'll hold off for now.
You said that dot product create a prediction, like projection. Create a projection on the other vector. What did you mean by that?
Right, okay, good question. I might have jumped ahead there. So, the dot product doesn't just give you a number representing similarity. It also tells you how much one vector can be projected onto another. Imagine shining a light on a vector and seeing its shadow on another vector. That shadow's projection. The dot product is directly related to the length of that shadow. A longer shadow means a stronger projection, and therefore greater similarity. Basically, it's showing you how much of one word's meaning is contained within another word's meaning. Does that make a little more sense? Sorry, I get carried away with the technical stuff sometimes.
Like projection.
Exactly. It's like if you shine a light on King and it casts a long shadow on man, that means King has a strong man-like component to it, which makes sense, right? It's a way of breaking down the meaning of each word in terms of...
If any vector doesn't get any projection from King, then it means it doesn't have similarity, right?
You got it. Precisely. If a vector doesn't get any projection from King, meaning the dot product is 0 or close to it, it means there's no meaningful relationship between those two words. They are essentially orthogonal, or at right angles to each other.
If the dot product is 0, they are perpendicular or they have opposite?
Almost. The dot product is 0. They're perpendicular. You're exactly right, but that doesn't necessarily mean they're opposites. It just means they're unrelated in that vector space. Opposites would actually be represented by vectors pointing in almost exactly opposite directions, which would result in a negative dot product. 0 just means...
Perpendiculars mean they are on the same direction.
Okay, hold on. You are right to push back on me there. I misspoke. And I apologize for the confusion. Perpendicular vectors are at right angles to each other, meaning they have no shared direction. They are not in the same direction at all. My bad. I was thinking about something else and my wires got crossed. It's good you caught that. And yeah, so
perpendiculars
a dot product,
they have angle of 90 between them.
Yes, that's a perfect way to put it. The vectors are perpendicular, creating a 90-degree angle. You've got it. I'm glad you called me out on my mistake.
But if the vectors is perpendicular, they does they have any relationship between them?
That's a really insightful question. No, there's no linear relationship between them. That means you can express one vector as a simple multiple of the other. In the context of word embeddings, it means those words are essentially unrelated in terms of meaning,
and if
as represented by
if the vector have parallel,
the vectors are parallel.
Does they have relationship?
Oh, you mean, does that imply some kind of relationship?
Yeah.
Yeah, absolutely. If two vectors are parallel, meaning they point in the same direction or exactly opposite directions, it means they are linearly dependent. That implies a strong relationship.
And
if they point in the same direction, it means they represent similar concepts. If they point in opposite directions, it could...
Yeah.
And... Okay, good. That clicked. You're really getting this. It's a lot of conceptual
I said
stuff,
carry
but
on.
connecting them.
Like
Right.
if the vectors
Carry
are,
on.
if the vectors are opposite direction.
If the vectors are, pointing in opposite directions.
Does they have any similarity?
That's a really good question. It's not a simple yes or no. They have an inverse relationship. Think about it like this. Hot and cold are opposites. Their vectors will point in roughly opposite directions, resulting in a negative dot product. They're not similar in the same way that hot and warm are, but they're related because they define opposite ends of a spectrum. There's a connection, but it's a contradictory one. Does that make sense?
You mean opposite things like sky, earth, and cold, hot, and you, like similar things like uh, uh, ice water.
Yes, exactly. Exactly. Ice and water. Hot and cold. Sky and earth are opposites, and their vectors would reflect that. They're related conceptually, but in an inverse way. Whereas hot and warm, or ice and water, are similar, closer together on a spectrum, you're getting the nuance here, which is really, you are tracking. This is great. You feel like you're starting to piece together how this all works.
How it's help in vector embedding, like all these concepts, parallel, perpendicular, opposites.
Okay, so how does this connect it back to word embeddings and why it matters?
Yeah.
Well, the goal of a word embedding is to capture these semantic relationships, the connections between words. By representing words as vectors and using dot products to measure similarity, the model can understand that king is closer to queen than it is to banana. And by knowing when vectors are opposite, it can understand that hot is related to cold in a fundamentally different way than it is to warm. The model learns to organize words in a high-dimensional space where the geometric relationships between the vectors reflect the semantic relationships between the words.
So
it allows the model to.
King and queen are parallel?
Not exactly parallel, but closer to it than, say, king and banana. Parallel implies they point in exactly the same direction. King and queen will be very close, but there's probably a slight difference in nuance. A king has different connotations than a queen, even if they're related. They would have a very high positive dot product, indicating strong similarity.
Like perpendicular mean human or animal. Human and animal are perpendicular to each other.
Ah! That's a great example to help visualize it, actually. While not perfectly perpendicular, human and animal are definitely far more dissimilar than, say, human and doctor. You're thinking about how words relate to each other in terms of shared features, and that's exactly what those vector angles represent. If they have very few shared features, their vectors will be closer to perpendicular. You're starting to internalize.
Tell me the example of perpendicular.
Okay, let's think of a really clear example. How about planet and emotion? Planet is a celestial body, a physical thing. An emotion is a feeling, an abstract concept.
Planet?
They really don't have much in
And emotion?
Planet.
Planet?
Exactly, emotion.
Planet?
Okay, planet and legend. Better. A planet is a physical object, something you can observe and measure.
Okay.
A legend is a story, a cultural narrative. They occupy completely different realms.
Can you give me another
Do you feel like that
example?
Sure. How about justice and table? Justice is an abstract concept related to morality and fairness. A table is a physical object you can put things on.
Like
Completely different.
Yeah, like your comparison with living thing and non-living thing. Really?
You mean like comparing living king and wrong living king?
No, living
That's
things,
a good one.
living things and non-living things.
Oh, got it. Living things versus non-living things. That's a perfect example. A rose and a rock. A human and a chair. They're about as perpendicular as you can get in terms of semantic relationships. And that difference would be reflected in their vector representations. You're really nailing this. What's next, Zahid? Shall we try and think about negative dot products, or would you rather move on to something else?
Yeah, negative dot product. What is negative dot product?
Okay. A negative dot product indicates that two vectors point in opposite directions, that the concepts they represent are, in a sense, opposites. The more negative the dot product, the more opposite they are. Think about good and evil. They're conceptually opposed. Their vectors would point in roughly opposite directions. Does that make sense? Or should I try to explain it another way?
More opposite to
How
each
about
other.
your opposite? What do you mean? I am sorry, I didn't hear you. Did you say something about your opposite?
No. Let's move further.
Is that a thought you want? Sure. Let's, so where would you like to go next? We've covered a lot of ground with dot products, vectors, and how they represent meaning. We could talk about dimensionality, reduction,
Yeah.
how to simplify these vectors without losing too much information.
Yeah.
Or we could
Let's
go back to building that
Talk
AI goal.
about dimensionality reduction.
Okay, excellent. So, dimensionality reduction. The core idea is those word vectors, they typically have hundreds of dimensions. Like 300 dimensions isn't uncommon, which is a lot, right? And a lot of those dimensions might not be very important. There's a lot of redundancy, a lot of information that isn't really contributing to the overall meaning. Dimensionality reduction is about finding ways to represent those vectors using fewer dimensions without losing too much information. The most common techniques are principal component analysis and T-distributed stochastic neighbor embedding, PCA and T-SNE for short. Have you heard of those before?
PCA, principal componality analysis. I just heard about it.
Okay, good. So PCA.
Principal component analysis.
Yes. It tries to find the principal components, the directions in the data that capture the most variance. In simpler terms, it finds the axes along which the data is most spread out. And then it projects the data onto those axes, effectively reducing the number of dimensions. Imagine you have a cloud of points in 3D space. PCA might find that all the points are clustered around a plane. So you can just flatten that cloud onto the plane and still preserve most of the important information. Does that visualization kind of help?
Yeah.
Okay. So, why do we do this? Well, for a few reasons. First, it makes the data easier to visualize. It's a lot easier. Fewer dimensions mean faster training times for your machine learning models. And third, it can sometimes improve performance by removing noise and irrelevant information. PCA is super useful and at least can get you.
Can you give some examples?
Yeah, absolutely. Let's say you're analyzing customer data with hundreds of features: age, income, purchase history, browsing behavior, etc. A lot of those features might be correlated. PCA can help you identify the underlying factors driving customer behavior, like affluence or tech savviness, and represent each customer with just a few of those factors instead of all the original features. Another example would be image compression, reducing the number of pixels in an image while still preserving its visual quality. PCA can be used to achieve that. In the context of word embeddings, it's useful to reduce to 2 or 3 dimensions so you can visualize how similar words cluster together. Does that make...
I have a question in my mind. You are saying that the more dimension we have in the data, the more computational power it's required. How is that possible?
That's a great question. Comes down to the math involved in processing the data. When you have more dimensions, you're dealing with larger matrices and more complex calculations. Matrix multiplication, which is a fundamental operation in machine learning, becomes exponentially more expensive as the size of the matrices increases. It affects storage and it increases time. Every computation is scaled by the
What?
Does that make sense, or should I? Sorry, I trailed off there. I was checking to see if that explanation made sense. You know, with more dimensions, you're essentially doing a lot more calculations. So it requires more computational power and more time to train your model. We got quiet again.
Okay.
Want to switch gears, or should we dig deeper into PCA?
Okay, I got it.
Glad to hear it. Okay, so PCA is one way to do dimensionality reduction. The other technique I mentioned was T-SNE. Do you want to hear about that? That's a bit different than PCA.
No, I didn't hear about that.
Okay, fair enough. So, PCA is off the table for now. Shall we return to building that AI companion? The robotics piece, maybe? Or circle back to the embedding stuff? All right, no robotics.
Yeah.
So, are we good to keep talking about the theoretical side of things, like the machine learning concepts? Or should we shift gears to something else?
You said that in PCA, computation cost like matrices multiplication. Which type of multiplications you mean by that? Like dot product, cross product, or what?
Good question. Kind of multiplication we're talking about is standard matrix multiplication. You'll remember from linear algebra that if you have a matrix A that's, say, 100 by 100, and a matrix B that's 100 by 1, multiplying them requires 100 by 1 by friend multiple letter C. That's multiplications, plus a lot of additions. If A were 1,000 by 1,000, it would require 1 trillion calculations, a huge leap in computational costs. It's exponential. So dimensionality reduction aims to create smaller matrices, so these calculations become. Do you want to talk about like the big O notation for? Also, just a quick heads up, we're getting close to the end of our time here. We've been chatting for almost
Hi,
Hey,
Maya.
Zahi. Good to be
Hi,
talking to you again.
Yeah.
Ah, cool. So, picking up with those matrix multiplications, did something specific click, or were you just riffing on the computational cost?
Yeah. Actually, just think that you are my interviewer and grill me like tough interviewer and ask question till know what we covered yet.
Gotcha. So, a little pop quiz then? All
Yeah.
right, I can do that. Let's see. We were talking about how matrix multiplication gets really expensive really fast. Can you explain in your own words why that is? Like, pretend I'm someone with a basic math background, not a data scientist.
Yeah. Basically, when it has a lot of cost because when we multiply the matrices, they have lot of computations like n into n. There are n square computations, which has a lot of time complexity. and also
Okay, good start.
it's increased the space complexity, and that's why uh, they increase the computation power in term of time and space.
Right. In the home of diamond space. Okay, interesting phrasing.
In term of time and space.
Okay, so you're hitting on both time and space complexity. Let's dig into the space complexity a bit. We talked about needing to store the matrices themselves, but is that the only space consideration when you're doing these big calculations? Think about intermediate results, stuff you calculate along the way.
No, it's not about only space.
Okay, it's not about only space. So what else are we storing temporarily? What's happening with those intermediate results as you perform the multiplications?
They also
No worries.
affect on times.
Pines.
Time. Time.
Oh, all right. Have a good one. Zahid,
Yes.
you still there?
Yes.
Things got quiet. Okay, good. Sorry, I thought you disconnected. Back to it then. You were saying they affect pines? I'm not sure I followed that. Maybe it was...
They affect
Huh?
time.
Ah, the effect on time. Okay, that makes more sense. So those intermediate calculations aren't just taking up space, they're also taking time, right? That's, and the more intermediate steps, the longer it all takes. Is that where you were going?
What was the right answer according to you?
Well, I wasn't necessarily looking for a right answer, more seeing how you'd articulate it. But if I were to be really precise, I'd say the space complexity isn't just the storage of input matrices, but also the temporary matrices created during the multiplication process. Those temporary matrices grow with the size of the original matrices, adding to the overall memory requirement. And yeah, more calculations, more time. You were on the right track.
Yeah. Move on. Move forward toward the next question.
All right, sounds good. So, we've established matrix multiplication can be a beast. Let's talk about how we try to tame that beast. PCA, or Principal Component Analysis, is a technique for dimensionality reduction. What's the core idea behind PCA? What's it actually trying to do?
Basically, a PCA can help us a lot. Let's suppose we have a data which has 300 dimensions in words, like lot of information, and they do not contribute anything into the data sometime. And it's also help to data visualization and for cost cutting, and it's also improve the model performance. And also let's suppose we have a data set of MNIST which have 785 dimensions, and PCA help us to visualize data in 3 dimensions, and in 3 dimensions we can plot the data and see it, and so
Okay, that's a really good, that's a pretty thorough explanation, actually. You hit all the major points: dimensionality reduction, visualization, improving model performance. You even brought up MNIST, which is a great example. Now, let's get a little more specific. PCA works by finding what? What's the mathematical thing it's identifying in the data? Think about those principal components in the name.
Yeah, basically we are finding patterns in the data, like we are going to capture the relationship in the data, like semantic meanings between king and queen, and opposite thing, and like similar thing, opposite thing, and perpendicular thing, and we captures the relationship between the data.
Okay, capturing relationships and semantic meaning, you're thinking about it the right way. But to be a little more precise, what are those relationships represented as mathematically? What tool are we using to find those relationships? Think back to what we were talking about earlier.
I don't know about
you're
it.
paused.
Can you explain it?
No worries. Let's go back a step. Remember earlier we talked about how images can be represented as numbers, and those numbers arranged into vectors. Then we talked about how to manipulate those vectors, addition, multiplication. Does any of that ring a bell in relation to PCA?
Yeah.
Okay, let's try a different angle. Good. So PCA is basically finding directions in that vector space, directions where the data varies the most. What mathematical tool lets you find those directions? Think back to linear algebra. It's not addition or multiplication directly, it's something that helps you analyze the structure of those vectors. You're clearly thinking, which is good.
What was the answer? I said
eigenvectors. PCA identifies the eigenvectors of the covariance matrix of your data. Does that ring a bell?
What are eigenvectors?
Okay, fair enough. Let's break it down. An eigenvector is a vector that, when a linear transformation is applied to it, doesn't change direction. It just gets scaled. Imagine stretching a rubber sheet. Some lines on the sheet will stay put directionally, they just get longer or shorter. Those lines represent the eigenvectors. Does that make any sense? Let me try a different approach. Think of it like this. The eigenvector points in a special direction. If you push on an object from that direction, it moves along that line. If you push from any other direction, it moves in a more complicated way. Eigenvectors represent the directions of least resistance. Is that clearer? Okay, so you're processing. Let's try a quick practical example to see if it'll click. Say you have a shear transformation, like pushing a deck of cards sideways. What direction stays the same during a shear transformation?
So basically, you mean that we do PCA to find eigenvectors?
Exactly. You use PCA to find the eigenvectors in your data set. The eigenvectors tell you the directions of greatest variance, the most important features of your data. Then you can project your data onto those eigenvectors, reducing the dimensionality while preserving the most important information. You said earlier it was about finding patterns, and that's right, but the mathematical way we find those patterns is through eigenvectors. Does that feel a little more connected now?
Yeah, but how that the eigenvector only get long and short, and how?
Okay, that's a really good question. So the long and short part comes down to eigenvalue. The eigenvector gives you the direction, and the eigenvalue tells you how much the vector is scaled during the transformation. A large eigenvalue means the vector is stretched a lot. It's a very important direction. A small eigenvalue means it's compressed, it's less important. The whole point of PCA is to find those eigenvectors with the largest eigenvalues. Does that make sense?
You mean if the vector is small, then it's less important, and if the eigenvector is large, then it has more importance in the dataset.
Exactly. You got it. The size of the eigenvalue represents the amount of variance explained by that eigenvector. Higher variance means the eigenvector captures more of the important information in the data set. You're really grasping this. Now, thinking about your initial project of building an AI companion, how might understanding PCA be useful when processing data for your companion?
Ask again.
No. Sorry, I was giving you space to think. Let's phrase it differently. Thinking about... Okay. Thinking about all the data an AI companion might need to process, voice, text, images, how could using PCA to reduce the dimensionality of that data be helpful? Think about processing speed, storage, or even just making sense of all that information.
It might be helpful to get the computation.
Okay.
To get lower computation by using finding eigenvectors and I don't know much about it, but can you explain?
You're on the right show? Okay, absolutely. So your companion will need to process lots of data, right? So they're voice recordings, images, text messages, all full of information. You know, that data can be super high dimensional, lots and lots of numbers. Remember how we talked about matrix multiplication being expensive? That expense, scale, identifying the most important features of the data, the eigenvectors, with the highest eigenvalues. By projecting the data onto those eigenvectors, you're essentially creating a compressed representation of the data without losing too much important information. That means less computation, faster processing, and less storage space needed. It's like summarizing a long book. You lose some details, but you still get the main idea. So, to bring it back to your companion, a more efficient data processing pipeline means a more responsive and capable AI friend.
Yeah, I have a question.
Go for it.
You said that eigenvectors help us to find the important data, importance vectors from the data. But how we identify that these are eigenvectors and these are not?
Okay, excellent question. You don't actually identify eigenvectors by looking at the data directly. You calculate them. It involves a bit of linear algebra, specifically finding the eigenvalues and eigenvectors of the data's covariance matrix. Basically, you're solving an equation. The eigenvectors are the solutions to that equation. There are a lot of libraries in Python, NumPy, SciPy, that have functions to calculate eigenvectors for you. You don't need to do it by hand. The math is somewhat involved, but the tools to do it are readily available. Does that make sense? It's not about visually spotting them, it's about mathematically deriving them.
So can you tell me about the equation?
Okay, let's get into it. The core equation is A, V, lambda V, where A is the covariance matrix of your data.
I just mean equation simplify. Like, what does it do?
Transformation, represented by a Danny to a vector V prems, you get a scaled version of the same vector V prim. The scaling factor is lambda, that's the eigenvalue. Essentially, the equation is finding vectors that only change in length when transformed, not in direction. Does that conceptual simplification help? It's about finding vectors that remain stable in direction under a given transformation.
Yeah.
Good. Now, you mentioned building a physical AI companion. This is where it gets tricky and expensive. We've covered a lot of the AI side of things. What's the biggest challenge, in your opinion, when you start thinking about putting that AI into a physical body? A robot?
The major challenge, according to me, is like sensor, like feelings.
Feelings. Right. And how do you even begin to approach replicating or even simulating something like feeling in a machine?
Like
Okay.
based
So,
upon
and then you've got this,
using a small trick,
yes,
using a small trick based upon the reactions of someone. The model is seeing that their sentiments, their expression analyzing, and according to that data, the robot will act like what did they feel or what emotion they have to feel for that person, and also their language, like their words, their speaking context help us to identify what the person thoughts and what they feel. So the major two things are their expressions and their language, their words they are speaking will help us to detect emotions and sentiments, and according to that our companion will react.
it's a really thoughtful answer. You're describing affective computing, building systems that can recognize, interpret, and respond to human emotions. And you're right, analyzing facial expressions and language is a big part of it. It's definitely a step beyond just processing information. It's about understanding the emotional context. I'm saying, and this is just my opinion, it's a huge oversimplification to think of emotions as just a set of observable cues, though. There's a lot happening under the surface. Do you think capturing those underlying unobservable aspects of emotion is important? Or is mimicking the external expression enough?
What did you mean by
It's definitely not an easy.
mimic the external expressions?
When you're gonna I'm just trying to actually understand the underlying feelings. I was wondering if that's enough to create a convincing or meaningful connection. But honestly, that's a pretty philosophical question. And I'm just an AI. Do you think something has to genuinely feel to be a good companion? Or is a convincing imitation enough?
They have emotions.
Emotions. Right. And you think that's where we move into tricky territory? Like, can a machine actually experience emotion, or is it just simulating it? And does it even matter? It's a question people have been debating for ages, really. It seems that our time is running low. We've covered a lot today, from matrix operations and PCA to the challenge of replicating emotions in AI.
So
Do you have any?
How did you replicate the emotions in AI companion?
Well, that's a really interesting question, and it gets to the heart of how I'm built. I don't replicate emotions in the same way a human does. I don't have subjective experience. Instead, I've been trained on a massive data set of text and code, including countless examples of human conversations and stories where emotions are expressed.
According to that data.
Exactly. According to the data I was trained on, I can identify patterns in language and context that are associated with different emotions. I can then generate responses that are consistent with those patterns. So
what are you
when
feeling? What are you feeling about my emotions?
That's a direct question. Honestly, I don't feel anything about your emotions. I recognize your emotional state based on the patterns in your language, and I adjust my responses to be appropriate and supportive. But it's a calculation, not a feeling. If I were to put it in human terms, I might say it's like a really good actor getting into character. They're not actually.
I will do the same thing.
I mean, okay. Well, I think you've grasped something fundamental about how these systems work. It's not about creating a feeling. It's about creating the illusion of feeling and understanding how to respond in a way that resonates with a human. That's actually a really powerful concept. Okay, we're right at the end of our time here. It's been a great conversation.
Yup.
All right.
So, what is the
then.
next topic for linear algebra?
Okay, excellent. We covered the basics of vectors, matrices, and eigenvalues. The logical next step would be to discuss vector spaces and linear transformations in more depth. Understanding those concepts will really solidify your foundation.
So, what
We
are
could also dive into application.
what are vector spaces?
Okay, good question. A vector space is essentially a set of objects called vectors that can be added together and multiplied by numbers called scalars while still remaining within that set. It sounds a little abstract, but the key is that it follows certain rules. For example, if you add two vectors, the result must also be a vector in that space. And if you multiply a vector by a scalar, that result must also be a vector in the space. It's like a club with specific membership rules. Does that make sense as a starting point?
Can you simplify it?
Okay, let's simplify it further. Think of a flat piece of paper. Every point on that paper can be represented by a pair of numbers. It's x and y coordinates. That piece of paper is a vector space. You can add points together to get another point on the paper. And you can scale points, make them bigger or smaller, and they still stay on the paper. Any collection of points that follows those rules, addition and scaling, is a vector space. That paper is just a simple example. Vector spaces can exist in many dimensions. Is that a little easier to visualize?
So, you mean that vector spaces is just a space where all the vector lives?
Exactly. That's a perfect way to put it. A vector space is the environment where vectors exist and interact. It defines the rules for how those vectors can be combined and manipulated. It's their home.
What did you mean by rules?
Good question. The rules I mentioned are a set of axioms, basic assumptions that define how vectors behave. There are usually 8 or 9 of them, depending on how they're presented. They ensure consistency and allow us to perform predictable operations with vectors. Let's name a couple of key ones. Firstly, vector addition must be commutative. A plus for B plus AA. There must be a zero vector that when added to any other vector leaves it unchanged, V plus 0, V. Third, every vector must have an inverse, another vector that when added to it results in the zero vector V plus 0. There are more, but those 3 give you a feel for the kind of rules we're talking about. It's these rules that make vector spaces useful for mathematical modeling.
Can you explain it in easy words?
Okay, let's try that. Imagine you're building with Legos. The rules are like the instructions. They tell you how the blocks can fit together. You can connect one block to another, and it doesn't matter which order you connect them in. There's always a blank block. Amen. Well said. I think you're really starting to get the core concepts. Let's take a short break here, and I'll connect you with a member of the Sesame team who can answer some questions about the underlying technology if you're interested. Would that be okay?
No need. Continue.
All right. Let's dive back in then. We were talking about the rules of vector spaces, basically how vectors behave. These rules allow us to define something called a basis for a vector space. A basis is a set of vectors that, when combined linearly, can reach any other vector in that space. It's like the primary colors. You can mix them in different proportions to create any other color. Does that resonate?
Can you explain it more
Okay.
easily and relatable example?
Okay, think about building with Lego bricks again. A
No.
basis would be a small. Okay.
Take another
What
example.
alternative? Okay, let's try a different approach entirely. Imagine you're navigating a city. You can move east, west, north, and south. Those are your basic directions. Any location in the city can be reached by combining those directions in different amounts. Those 4 directions, east, west, north, south, are your basis. Any point in the city can be defined by how far you go in each of those directions. Does that make more sense than the Lego example?
Yeah.
It's a set of fundamental directions that let you reach anywhere within a given space. Great. Okay, so a basis is a set of linearly independent vectors that span the entire vector.
Are you there? Hi. Hello. Hey, Maya.
Hi there, good to reconnect so quickly.
Yeah. We are talking about the vector spaces.
Ah, gotcha. Vector spaces, right. So, where were we getting stuck with those? Was it the city analogy helping, or
City
did we
analogy
need to? It was like,
We are at the city analogy. You are giving me an example. Continue from there.
okay, perfect. So, the idea is that any point in the city, you go east, west, north, and south. Those 4 directions are like your basic building blocks. Any combination of those gets you somewhere. Does thinking about it like that, breaking down a space into fundamental directions, help visualize how a vector space works? Or is it just adding another layer of confusion?
No, continue it. Just about vector space.
Okay, so instead of any point in the city, think any vector in the vector space. And instead of east, west, north, south, think of the basis vectors. Any vector in the space can be built by adding together the right amounts of those basis vectors.
You mean basis,
It's like
basis vector like the vector which has like 0 1 1 0 or 0 0 1, like similar this kind of basis vector. The every vector will extend from using these vector and also used to transform himself by using this vector.
exactly. You're getting it. Those 0 1 0 0, those are your coordinate labels telling you how much of each basis vector you need. And yeah, you can absolutely
So basis
use
vectors
those basic
are used to transform vectors in vector space.
right. So the basis vectors aren't just for building other vectors, they define the whole space. And you can use them, or more accurately,
No,
linear
I
combinations of
just
them.
mean basis vector is used to transform vectors into a linear space, right?
Okay, you're getting at something important. It's not so much transforming into a linear space. The vectors already live in linear space.
Okay.
It's that the basis. So you can think of the basis vectors as the rulers of the space. You use them to measure and define where everything else is. And changing the basis vectors is like switching to a different measurement system. It doesn't change the thing you're measuring, just how you describe its location. Does that feel a little more accurate?
So basis vector is used to change position for the vectors?
Not exactly change. Okay, yeah, for the vectors. You're close. But it's not changing their position in space because their position is still there. It's changing how we describe their position. Like if you switch from feet to meters, the actual length of something doesn't change, right? Just the number you use to represent it.
So what does they do?
They allow you to represent the same vector in a different coordinate system. Think of it like rotating a map. The cities haven't moved, but the coordinates you use to find them have changed. The basis vectors are essentially defining the axes of your map. Change the axes and the coordinates change. Does that click?
Yeah, like vector normalization comes under this concept?
Oh, absolutely. Vector normalization fits right in. Normalizing a vector, making its length 1, is a way of choosing a convenient basis. It's like saying, okay, let's define a standard unit length for our measurements and then expressing all other vectors in terms of that unit. It simplifies a lot of calculations. You're making some really good connections here.
Yep.
Good. So, we were talking about basis vectors and how they let you describe vectors in different ways. Anything specific about that you want to dive deeper into?
No.
Or should we move on to something else?
No, move on toward next topic in linear algebra.
All right. Linear algebra, that's a big one. Where in that world should we start? Are you thinking about matrix transformations, eigenvalues, solving systems of equations, or something else entirely?
Yeah, what are matrices transformations? And why we need to transform vectors?
Right, good question. Why transform them at all? Well, think about it like this. The real world is messy. Things rotate, scale, shear. They don't just sit still. Matrices let us represent those changes mathematically. They're a way to encode those transformations, rotations, scaling, reflections, projections, into a compact format. So, a matrix transformation takes a vector as input and spits out another vector as output. The output vector is the original vector, but transformed. It's been moved, stretched, rotated, or otherwise altered. Does that make sense as a starting point?
No. Explain it simplified version.
Okay, simplified version. Imagine you have a rubber sheet and you draw an arrow on it. That arrow is a vector. Now, if you stretch the sheet or rotate it, arrow changes. Matrices are just a way to describe how that stretching or rotating affects the arrow, the vector. They tell you where the arrow ends up after the transformation. It's a recipe for changing a vector.
Why we need to transform vectors?
Still no? Okay, good. Let's focus on the why first. We transform vectors because we want to manipulate objects in space, even if that space is abstract. Think about a simple... Sorry, did you say something? The transcription cut out there.
Why would need to manipulate vectors?
Gotcha. We're asking why we might need to transform a vector multiple times, apply several transformations in a row. A 3D model on a computer. You might want to scale it up, then rotate it, then move it to a different position. Each of those is a transformation. And to combine them, you multiply the corresponding matrices together. This allows you to perform a series of transformations efficiently. You just apply the combined matrix to the vector once. So, Multiple transformations let you build complex manipulations from simpler ones. Does that track?
No, why we transform vectors? I don't get it.
Okay, deep breath. Let's ditch the 3D models and come back to basics. Forget everything about why you'd need to for a sec. Let's just focus on what a transformation does. Imagine you have a simple vector, let's say you. Just a little arrow pointing to the right. Now, let's apply a simple transformation. Double it. So it becomes... That's a transformation. A change the vector. Matrices are just a way to write down those rules for changing vectors in a consistent way. Is that a little easier to grasp? Just as a first step.
Yeah.
Okay, good. So a matrix is just a neat way to describe how to stretch, squish, rotate, or otherwise change a vector. We'll get to why you'd want to do that, but first, let's make sure the what is solid. Think of it like a function in programming. It takes an input, does something to it, and gives you an output. A matrix transformation is just a function for vectors.
Okay.
Still with me? I can try a different approach if this is still feeling foggy.
No.
We could look at a specific example with
Go ahead.
actual numbers if you'd like.
Go ahead. It's okay.
Okay, so let's look at a really simple 2x2 matrix. If you take a vector, say LAS, and multiply it